Simply put, osmosis refers to the movement of water across a membrane to even out the solute concentrations on either side. While water molecules move back and forth randomly across the membrane, different concentrations of solutes, molecules dissolved in the water, on either side of the membrane cause a net movement of water to one side of the membrane to even out solute concentrations. This net movement of particles across a membrane based on concentrations and other factors is known as diffusion, and the diffusion of water is what we call osmosis. Water potential is a way of measuring the tendency of water to move to one side of a membrane or the other. We can use a combination of solute concentrations and pressure to calculate a numerical value for water potential, which I'll explain how to do soon. This number can be thought of as a measure of the potential for water to move away from a given side of a membrane. This means that if we know the water potential on both sides of the membrane, we know that the water will move to the side with a lower water potential. This is similar to how any system will move from a high potential energy to a lower potential energy. So for example, if we know the water potential on the left side, written as the Greek letter psi, is negative 1.5 bars, and the water potential on the right side is negative 2 bars, the right side has a lower water potential, so more water will move to the right side, away from the left. Remember that this only describes the net movement of water. Individual molecules will still move in both directions randomly. This is the equation for calculating the water potential on one side of a membrane. The equation itself is pretty simple. The water potential is just the sum of the pressure potential and the solute potential. Note that all three of these values are in units of pressure, such as bars. The pressure potential in an open container will always be zero. Otherwise, it will probably be given directly, although it should be converted to the appropriate pressure units to be added to the solute potential. A non-zero pressure potential would often be caused by a plant cell wall keeping pressure on a plant cell to prevent it from taking up too much water. The pressure half of the equation means that as the pressure potential increases, the water potential will increase, meaning that water is more likely to move away from that side of the membrane. This makes sense because applying more pressure essentially squeezes out the water. Calculating the solute potential is a little more complicated. This is the equation for solute potential. I'll start by explaining R. This is the pressure constant and is always equal to 0.0831 liter bars per mole Kelvin. These units are important because we will need them to cancel out with the other parts of the equation to give us a pressure value, usually in bars. T is the temperature. This should be in Kelvin, so the units cancel with the pressure constant. C is the concentration of solute, which we'll want to get in units of moles per liter. Finally, I is the ionization constant. This refers to how many particles the solute breaks into when dissolved in water. For covalent compounds, such as sucrose, this will be 1 because they do not break apart in water. Ionic compounds like sodium chloride will break into separate ions. Sodium chloride will split into 2 separate ions, one sodium ion and one chloride ion, so the ionization constant for sodium chloride is 2. Note that this value is unitless. Now going back to the overall equation, we can see why the solute potential part makes sense. The higher our values for C, the more negative the solute potential will be, making the water potential lower. Because water goes toward the side with lower water potential, this makes sense, as water will move to the side with more solute particles to even out the concentrations of solute by diluting the side with more solute. Okay, now let's work through a problem using water potential. We are given that the water potential outside of the cell is negative 1.5 bars. Now we'll calculate the water potential inside the cell and compare the two water potentials to figure out which direction the net movement of water will be. Pause the video if you want to try for yourself. Okay, so we are given a pressure potential of 25 pounds per square inch. We'll want to convert that to bars so we can add it to our solute potential later and compare it to our water potential for the other side. We can do this by multiplying by the ratio of 1 bar per about 14.5 pounds per square inch, giving a pressure potential of roughly 1.7 bars. For the solute potential, we have an ionization constant of 1, as sucrose does not break down in water. Our concentration is 0.1 molar sucrose. Molarity is the same as moles per liter, which will help our units cancel with the pressure constant, which we'll put in now. Our temperature is 20 degrees Celsius, which, adding 273, gives us 293 Kelvin. Canceling units and multiplying, we get a solute potential of about negative 2.4 bars. Adding this to the pressure potential gives us a water potential inside the cell of negative 0.7 bars. Now we can compare our water potentials. The water potential is lower on the outside of the cell, and as water moves from a high to low water potential, our net movement of water will be to the outside of the cell. And we're done. I hope this all made sense, and thank you for watching this explanation of osmosis and water potential.